About me. So, as I said, my name is Hubert Łępicki, I'm a local guy. I got some experience in programming. I work with web applications, mostly Ruby on Rails, and they suck, as we just said. Why is that? That was a joke. Yeah, that's true. Right. But today we're going to focus mostly on the server side. And you might find that weird because usually it's front-end that sucks, but as many examples show, web applications suck very much on the backend. And some of the error pages are nice, some nicer than the others. Something's clicking here. Some are really pretty, but generally, if that blows up bad. And that's something we want to avoid when we're building web applications. As I was preparing for the presentation yesterday, I took this screenshot that was afternoon after work hours. I noticed one of the client applications is misbehaving. So it was deployed to Heroku. I had a look at what's happening. I had a look at the code. I had a look at the requests that being sent back and forth. And I found this little issue. That's a part of Ruby on Rails application where we load notifications for the user. And the programmer who did that probably was me, didn't include any limit on the number of notifications that's going to be returned from the server to the front end. And everything was working fine until some heavy users started using the application on a daily basis. When they did, suddenly they had several thousand, I think 13,000 was the most, of unread notifications I found in the system per user. And those unread notifications were loaded to the client side where the paginator just displayed first page. That's a rookie mistake. Okay, that can happen. However, why everything exploded? So what exactly happened? One of the requests took a lot of time to process. It allocated a lot of memory, slowed request blocking the server. App became totally unresponsive, not just for that single user, but for all the other users into this application. Why? Let's have a look at the deployment. We got a pretty robust Heroku setup with two power dynamos. In total, they were using 16 instances of web server called Unicorn, and we could, in theory, handle 16 concurrent requests. That kind of sucks. It's only 16 concurrent requests being handled by the server at the same time. It only takes 16 requests, slow requests, to block the server for all the users, and that's what exactly happened. Why? Our stack is Ruby on Rails. Ruby is slow, and that's not a secret. When we deploy applications to Heroku or to other hosting providers, we basically have two main choices. One is Unicorn, which is what we used here. It's a web server that spans one worker, multiple workers that map to system level processes. And they can handle one request at a time. So they're not multi-threaded. And there's another web server which is very popular. It's called Puma. Puma works different way. It spans a pool of threads and distributes those requests among the threads. And Puma was actually our primary choice when we deployed the application. However, we stumbled across an issue unresolved since 2013 or 2012 in the web server, that it basically leaks memory. And it leaks memory like crazy. In our setup, we would have to restart the Puma server every hour or so. So this brings the memory of the very first raise deployments we did. Somewhere in 2009, 2008, where that was a standard practice. Maybe that's going back to the roots, I don't know. But basically, what's wrong? Why so many problems? This must be rocket science to build a reliable software. Is it rocket science? Maybe it is. Why is it so painful to build reliable web applications? When I think about it, I basically want to migrate, preferably to some alternative universe, where functional programming is a predominant way of writing software. So why in Ruby making that work is hard? Basically, we have shared data everywhere, within the framework, within the web server, within the middleware that's executed. And that's because of the majority of the programs. We don't have any built-in crash recovery mechanisms, so if one of the web servers, if one of the unicorns dies, it just dies. And, we don't want the unicorn to die. Just don't want to do that. The situation is even worse if you go with Puma server, which is threaded. Like, if it's going to run out of memory and exhaust all the system memory, it's just going to crash all threads, not just the one thread that it caused this issue. When you do this sort of threading or the shared mutable data and sort of applications, garbage collection is really hard. Like, it's difficult to implement, and we know that Ruby garbage collector is also slow. This is what's slowing down Ruby interpreter in many different cases. Creating threads and managing, synchronizing those threads from a programmer's point of view is really difficult. You have to use those mutexes, semaphores, or different logging mechanisms to do that, which are not very programming friendly. And once you created that thread, you have little control over what it does. You cannot say, or maybe, you cannot easily say, please hold on and let somebody else handle some work in the meantime. That's mostly the task for the operating system to schedule those threads. And sometimes we like just have a bit more of a control over what's happening. Moreover, monitoring is hard. So the errors I showed you on the one of the first slides, the stuff was happening yesterday, none of our monitoring tools detected that. We just got that from Heroku itself. Because these monitoring tools, they run inside the Ruby process that got basically killed. So that sucks. It makes one think that the world would have been way better if only there was a virtual machine that is taking care of all those things. Is there? Is it Java? It's certainly better than Ruby. In fact, there's a nice implementation of Ruby called JRuby that runs on top of Java, JVM, to be precise. And in many cases, it's faster, more reliable than traditional Ruby implementation. However, it's also quite inconvenient to use in many cases, slow in development. It provides you with some nice tools in theory like torclogs to deploy your applications on the so-called application server. In reality, I found there's little control of the programmer or designer of the application on how you can do stuff. You hit all those constraints of your environment and you still got little control over what's happening. Is it .NET? Maybe. I don't know. Is it Python? Maybe. I've heard good things about Python. So, what all of those virtual machines have in common? In 1971, Mr. Dijkstra came up with a task for their students, university students, to solve the problem of dynamic table servers. You're probably familiar with that problem. It's basically talks about 5 philosophers sitting at the round table, having only 5 forks to eat their meal, and they do need 2 forks each to eat the meal. So this is a problem of competing for resources that illustrates, for example, how processors compete for hard drive. And this problem can be solved in many cases, and it's quite difficult to solve, but that's solvable with mutexes semaphores. You can, however, write it in that way that quite easily get deadlocks, race conditions, or as any programmer's multi-threading problem, you can just run everything inside the critical section and don't care, just let one CPU do the work and waste all the others. And all those virtual machines, they do share the principles in common. Especially in the way we handle memory. So, I'm just going to tell you straight. It's the shared heap that is the source of all evil, and this is the reason why on all those machines, the same problems as they had in Ruby could have happened quite easily. Okay, quick recap from the primary school of programming. What's a stack? Stack is a part of the memory that is reserved. Once the function is being called, it puts its arguments on the stack, it puts their local variables in the stack, reserves a place for return value. When it calls another function, it does the same. When another function finishes, basically it pops from the stack. Those values are being popped from the stack, and the stack is being left free. In virtual machines, like Java virtual machine, they handle one stack per thread, so that the thread that executes it kind of knows where it is in the stack trace and what functions have been called so far. And that's a good approach that prevents mixing those data and separates those data. However, heap is the other data structure, place in the memory where the data is being allocated. This is where all of your dynamic data happens. When you create an array, it's being put in the heap. When you add a class to your classes, it's also being put on the heap. Basically everything that is dynamically allocated, or is, for example, classes, is being put on the heap. And heap is the place that's also being shared by the threads. So what is the problem here? The problem here is obviously the global state. The other problem, this first problem is the problem that you have to synchronize access to that shared data somehow, and make sure that there are no deadlocks, there are no other issues with it, there's no concurrency issues. However, there are other problems with that approach. It can be slow, so if you reserve some chunk of memory, and the computer processor wants to access that memory, to fetch that memory, it's not equal access time to all places in the memory. We have paging, so it's always better to access local memory that's close to each other when we're doing sequential reading from the memory. That's why, for example, you could have a two-dimensional array in Java, and iterating over goes slower. If you swap those variables, it might suddenly go faster. And it's also a single point of failure. And trying to clean up the heap from unused objects is actually rocket science. There are many PhD theses being written about different approaches, and I think Java comes with different strategies of how you clean up the heap and even tweak it to your application. However, there's an entirely different world of virtual machines. And entirely different virtual machine that I'm talking about is the airline virtual machine that's based on different principles. Okay, so what is Erlang? You probably heard the name. It's the programming language and environment runtime environment that exists since 1986. So I was like 1 year old when it was created. It's free and open source. It's proven in many battles. Like sometimes, when you hear stories about Erlang and how efficient and reliable it is, it's hard to believe. Like, for example, recently I've heard a story about WhatsApp running their application on single, very powerful, but still single web server, handling around 2 million concurrent TCP connections from the single machine. Those WhatsApp users sending themselves their naked pics, etc. It handled around 2 million requests quite easily. And obviously you're talking about it. So if you're making a phone call, it goes through Erlang systems, probably. One of the unique features of Erlang is the way it handles computers. There is no mutable state. There's only message passing. So you cannot share memory with other threads. They are called processes in Erlang. So if there's no shared memory, there's no problem, right? Of course, you have to design your application in a different way to accommodate for the lack of shared memory. But the basic principle is that there's shared nothing between processes. Okay, so how does it work? Erlang, internally, so actually not Erlang internally, but the programmer who programs the application splits the application into concurrent chunks of code, which are called processes. They are roughly equivalent threads. They're not real operating system threads. They are handled by the Erlang virtual machine. And those processes, they basically get a mailbox. They get their inbox where the messages land. They can also send messages in replies to messages, synchronously, asynchronously, or just message different processes by their reasoning. What is unique is how they store their memory. Instead of having one shared heap, every single Erlang process gets its own heap. That makes it easy, for example, to clean up after a process. If a process terminated, the Erlang virtual machine just scraps everything from the heap and from the stack. That also makes the data being sitting next to each other. So when the process executes, it probably is going to read from that memory that's next to each other rather than reaching out to different part of memory that's available in the system, which is good, makes it faster. Yeah, so this battle program on many devices, there's some different companies, they run Erlang. They basically have multiple processors inside, and they can, not very powerful processors, but there's a lot of them inside. So they can handle concurrent connections, for example, when you call. And they can all communicate through the message passing, and they are supervised, which is really important, by other processes that restore them, for example, in case of recovery, or take another action. Now, let's have a look at our computers, web servers of 2015. We also have multiple CPUs. Maybe we don't have hundreds of them, but we have 8, 16, 32, 64. We get plenty. We get tons of available memory, so this possibility of making requests to the memory that's not localized is very, very, very high. It looks like the hardware is perfect to run Erlang systems on. So why nobody wants to write this beautiful language? So what's wrong with Erlang? I hope there are no hardcore Erlang fans here. Alright, sorry. It's got pretty unfriendly syntax for newcomers. And unfamiliar technology. The other thing is that it's set in the functional mindset, right? So for programmers who are familiar with object-oriented programming, that is the mind shift. And it does require writing a lot of boilerplate code. So it doesn't come with good, for example, meta-programming technologies, so it doesn't allow you to write code that write code, which basically means you have to write a lot of stuff yourself. Alright, that's all about that. And that was the case until this guy came along. He had a look at what's Ruby programming like. He was Rails core manager for a while, and he, I guess, was frustrated with the state of things as much as I am, probably more. And he had a look, what's the best virtual machine I would like to run solid web applications on. He figured it's Erlang again. So he looked at the Erlang itself, and apparently he didn't enjoy it for some reason, or thought maybe that it can be better. So he created like new programming language, and while he was coding it in his hometown Cieszymy near Krakow, people were making fun of it, saying, hobby programming language. It turns out he was bloody serious about the whole thing. That's how Elixir came to be. And some people want to push really hard for this logo, for the mascot. I don't know, kind of looks familiar to me. I'm not sure where that was there from. But no, Elixir is very much alive. The community is growing very fast. It allows you to brew magical web applications already. I'm going to show you how in a second. Let's take a step back. What is Elixir? Elixir is a dynamic programming language that does have actually two ways of doing optional type checking. So for all of you statically typed languages fans, there's something to think about, even though in principle it's dynamic. It runs on an Erlang virtual machine. It integrates quite nicely with the Erlang ecosystem, so you can reuse these all amazing or less amazing libraries that accumulated in the Erlang ecosystem throughout those all years. It does provide you clean and easy to use syntax, really nice Erlang-based pattern matching, which is probably subject on the presentation itself. It's also functional. It has just a few data structures that are all immutable, and it's a compiled language. How does it look like? Oh, let's see that. It's a shame. Basically, it looks like Ruby. So that's somebody's phone. It does solve quite a few problems that Erlang has. For example, it comes from the great Unicode support, which is supported for building web applications. It's got really nice, I really like that feature, documentation built in, xdoc, where you basically comment the code in your modules or functions, and you can run the script that generates documentation for you. It comes with a basic yet functional testing framework included. And this is really a Swiss Army knife. This little command that gets installed once you install Elixir Mix. It's like a tool that allows you to perform various tasks, from starting a web server to compiling the project, installing dependencies, or running just a selected function from your modules. It does quite well with managing dependencies with heads. We also use that with Mix, that Mix types that fetches dependencies, installs and compiles them. We can talk to the database. There's a library called Ecto, which is roughly, it takes some ideas from both, I guess, Active Record or from Link in .NET, and some new ideas from its creators to how you can read and write stuff from relational and NoSQL databases as well. You can now build usable web applications with Elixir with just one small library called Plug. Plug is like Rack middleware in Ruby, or it's like WSGI in Python, where you can allows you to encapsulate some functionalities and build pipelines of methods and functions you could call to perform some tasks together. It's also an interface that talks to airline server that's called Hubert that handles the HTTP itself. For those of you who prefer bigger frameworks, there's really amazing framework coming up called Phoenix. It's a full stack web development framework where you basically install Phoenix. You get the joy of using Elixir on the back end, modern front end with, unfortunately, JavaScript. There's something called Elixir script in makings, which I guess looks up to Clojure and their amazing Clojure script, but that's not ready yet. So the choice of the front end technologies kind of skips Elixir for now. And we can use some really nice airline tools also to inspect and have a look at what's happening in our Elixir applications. That's one of the tools where you can just open the observer and inspect with a graphical user interface to what's happening inside, what are the applications running inside our virtual machine, what's their messaging queue, how they perform, whether there are some memory increase or the queues for messages are getting high and stuff like that, which is really convenient and a really nice way of having a look at your running virtual machine. You can look it up on production as well and inspect your production application in real time, so you can figure out which of the processes or applications is troubling. Right. One of the strengths of Elixir, in my opinion, is the meta-programming, or the way that you can do meta-programming in Elixir. If you guys know meta-programming in Ruby, for example, this is a completely different thing. So I guess it's closer to what you do in these dialects, where you treat a code as a data structure, manipulate it, to basically rewrite it and make it do different things. As I said, this is a functional language, so this code, for example, doesn't look functional. It doesn't look pretty standard like C or whatever, just sequential execution of commands. There's no state being returned from one function being passed to another. That doesn't look functional. So what this library, this is actually part of the web application I'm writing in Phoenix. What this router does is takes this code, looks at this code as it looks like on the abstract syntax tree of the commands that are being executed, those functions calls, and remaps them so they are actually doing what you can see, what should they be doing, so they should be calling each other in order to form a pipeline. And Elixir allows you to use this supervising mechanism from Erlang in easy way. So there's a set of predefined supervisors that are basically processes that can spawn and monitor how other processes are doing. And in case that one of their children fails, they take some action. There's a set of predefined actions to take, like strategies, what to do in case of a failure. Obvious one is, if it crashed, okay, restart it. But you can program your own as well to accommodate for your needs. In real life, when you're building a web application, or when your framework provided you with structure, there's already a tree of supervisors in place, so that your application, if it crashes in some place, the crash is localized as much as possible, so it doesn't do what my Ruby application did, like crash everything. And I think that's very important. It's very important that we minimize the damage that's being caused by the failure, because the failure is unavailable. Right. But what can we do in case, for example, there's a hardware failure? That's a tougher question. So, Erlang comes with an option to cluster your virtual machines. You can cluster virtual machines running on the same host, or cluster them running on the network. If you have a fast network, that's going to work just fine. Why? If you remember when we talked about how concurrency is being handled by Erlang, it's simply a message passing. So it doesn't really make much difference whether you're sending a message to a process that's local or you're sending a message to a process that's remote. It's the same principle. You might need to amend, for example, the way your application starts as initialized, so it's aware of other clusters, other nodes within the cluster, and can connect to them. However, the basic principle of how your application is built hasn't changed. It's still message passing. So it can be set up in a way that we get either load balancing or failover in case one of the servers dies, which makes us sleep a bit better at night, which is what we like, right? One of the other really cool features is real zero downtime deployments. I just tried it last week with Elixir. It requires some magic, but basically it works, and you can hot deploy the code, parts of your application, parts of your system, basically replacing the running applications in that manner that they're not gonna lose a single HTTP request. Which, if you try doing like zero downtime deployments in Ruby or other technologies, that's in theory that's the case, but rarely that succeeds. Sometimes those first requests are getting, they're slower, they need some time to warm up, or they're going to be missing totally. So with Elixir and Erlang, you can actually do proper zero downtime deployments, and nothing misses a single message. The thing that's really important for me is that you don't have to learn as much infrastructure to do those sort of systems where there's not only request response through HTTP, but there's like background processing, there's some messaging sending in the background, email sending, or maybe there's a scheduled cron jobs. When we do Ruby and Rails, you have to set up different technologies. It's usually the web server, then the proxy, then we get a rescue for background job processing. We got cron that calls rake tasks to execute Ruby commands. If you want to do WebSockets in Ruby, you basically don't do WebSockets in Ruby, just outsource it to some external service. In Elixir, you can do all those things from within your virtual machine. There are libraries or just write your own to handle some concurrent tasks, and that should work just fine. So, in a way, it's sort of like a Java application server, but without the load, plus performance and the flexibility, so you can set it up the way you really want your application to be set up. Right, two buzzwords for the end. First one is microservices. If you think about that architecture that Erlang and Elixir provide you, you're sort of building microservice-oriented infrastructure. There are little chunks of code, processes running, and they pass messages between each other through predefined protocol. There's little infrastructure you have to do, and they kind of look like microservices. There's also a way to contain those applications and reduce their permissions, so it kind of look like containers that cannot do anything they really want. Right, so if you guys are more interested in the language, want to actually try it and learn about the syntax, I didn't show you my syntax, I don't think that's really important. It looks like Ruby. But basically this is that site, just getting started, really easy. If you're more of a book reading guys, highly recommend these free books for you. Programming Elixir, that's a good read, by Dave Thomas. Elixir in Action, that goes a bit more deeper into how Elixir interacts with Erlang and the ecosystem, what actually is happening behind the scenes. And that's a new kid on the block, that's Programming Phoenix in beta, I think. Half-written book by Chris McCord, Bruce Payton, Joseph Elliott, creators of the framework. Yeah, it's half-written, but it gives a really good overview of how you start programming in Phoenix itself. Thank you very much. That's it. So the question was, how long does it take to learn Elixir? We actually did an experiment within the company, and we took 2 interns this year, and instead of teaching them Ruby, we taught them Elixir. They were programming their application within a week since they started, so they were either smart, but that's not that hard enough. Questions?
How about the tooling, IDs, and that kind of stuff?
So the question is about the tooling, especially IDs, right? I don't know. It's one of the languages you can write using your text editor and execute commands from the console. So exactly like in Ruby, you don't need ID. I don't know whether there's anything supports Elixir at this stage. Maybe Robert knows.